What are threads? Threads are basically let's say this is one address space. Threads are simultaneous so a thread is basically a control flow execution. So you can think of a thread as just executing one instruction after another. I execute one instruction, then I execute the second instruction, and so on. And that's what a program is, right? It just executes one statement after another. And then there can be a loop where it goes back and all that, and makes a function call, returns from a function call. So this is this whole business of executing a program or executing a control flow is a thread. Okay. So far we were talking about processes. A process is a thread and a private address space. So your program must be running in a private address space. So a process is basically a thread plus its address space. But it's possible, as I discussed last time, that multiple threads share the same address space, right? And we were looking at this example of, let's say, browser tabs, right? So we said, like, look, a browser is just one program, right? They're not separate programs really, but the same program can allow multiple threads to execute within the same address space. In this case, each thread should trust each other because they're sharing the address space. So if one thread writes something, the other thread will get affected with it. So they should trust each other, and they should know about the existence of each other. So they should coordinate with each other, right? As opposed to, let's say, I run a program called an editor, let's say VI, and a program called a compiler, let's say GCC. So these two programs don't need to know about each other's existence, right? They are running in their private address spaces. But if we are executing tabs as threads, then they need to know about each other's existence, right? It's possible to implement browser tabs also as processes, right? Each tab could have a separate process, in which case they don't need to know about each other. But we said that, look, you don't really need separate processes for different tabs in a browser. Right? Because if you have separate processes, then you are wasting that much extra memory, because each tab will need extra memory, extra copies of the same code, right? And they will not be able to share information with each other. So if one tab has loaded a page, let's say one tab has loaded the page, let's say the first tab has loaded IIT Delhi's website. And now the second tab also tries to load IIT Delhi's website. The nice thing is, because if they share the address space, if the first tab had pulled the contents of the IIT Delhi website and put it in a cache in its own memory, right? Then the second thread can use that cache. So it allows for very fast inter-process communication. One thread has put in some data, it has put it in its memory. The second thread can also access that memory. And so, that way things can become faster. And so it becomes, so one way to think about it is that threads enable very fast inter-process communication, right? Because threads are nothing but processes, but sharing address space. So now if you have two processes which share address space, they can really talk to each other in a very fast way. One thread can just write to a memory location, and another thread can read from that memory location, and you have established inter-process communication. Recall that in the case of processes, that's not possible because you have different address spaces, so you have to do pipes and that kind of thing. Okay. If there are any questions on threads, so let me just give you some examples where threads are used. All right. So let's say threads, some examples. So, I've been using this idea of browser tabs. Another example is, let's say, web server, right? So let's say IIT Delhi's web server is running, right? Now multiple requests are coming to the web server. Now, one way to handle these requests is that each time a request comes, you so let's say this is a web server and requests are coming to it. Request 1, request 2, right? And let's say more requests. So one way for the web server to do this is, let's say, oh, I got request 1. So it will first process request 1 fully before it starts processing request 2, right? So you can imagine if there are thousands of requests coming to the web server, then, and if I'm doing one request after another, the last request which came is going to have to wait for a long time, right? On the other hand, if all the requests could simultaneously start, right? So let's say one thread is serving one request. So one thread is serving one request, second thread is serving second request, third thread is serving third request. So all these threads can execute in parallel. Assuming your hardware has multiple resources, for example, it has a CPU or it has multiple CPUs, right? So then all these CPUs can simultaneously be servicing different threads, different requests. Similarly, one of the threads could be accessing the disk, another thread could be accessing the CPU, and so on. So your system can be better utilized, and as an end result, the end user will see the web page getting loaded faster, right? So threads are very commonly used in servers in general, but I'm using the example of web server. So if you want to, let's say, start any website, then you will probably use some kind of a web server, right? And whatever that web server is most likely using threads, right? So there are different ways to do this, but one of the very common ways to do this is threads, where you say that I'm going to have one thread serving one request, and multiple threads can continue in parallel. Okay. Now, what is the advantage of multiple threads continuing in parallel? The advantage is that you will have higher system utilization, because now multiple resources in the system can be active in parallel. Right? So if there are multiple CPUs, then all CPUs can be active in parallel, for example. Right? Or if there's a disk and there's a CPU and there's a network card, then all these three can be executing in parallel, for example. Right? On the other hand, if I didn't have threads, then I would have just one control flow transfer, and the request will come and the request will get buffered, and now this one thread is going to pick up one request, handle it, send an output, then pick the second request, and so on. Right? So picking one request and doing it is much slower, as opposed to having multiple hands that pick up the requests simultaneously and start working on them simultaneously. Right? So that's thread. What was the other way to do it? You could say, oh, why are we using threads? Why not just use processes? Right? So one way to do it is process 1 will handle request 1, process 2 will handle request 2, process 3 will handle request 3, and so on. Well, that's also a way. All right. And you have these processes running simultaneously in the system. And so once again, you can have a lot of utilization in your system. CPUs can become busy at the same time, and etc. But the problem with processes is that each process needs to also have an address space, private address space, right? So if you have a private address space, then that much memory is required, extra memory is required. So if you have 100 processes, then you'll make 100 copies of the same code, for example, right? Similarly, you will make 100 copies of the same data, which is used to implement the logic of the web server. Also, if two processes need to communicate with each other, it's very costly, right? In this case, in a web server, I'm using threads for requests. Then let's say there was a request that came from let's say IIT Bombay, and another request came from IIT Kanpur. Then let's say there was some amount of processing that was common to both these requests. So if one thread request has already performed that computation, the second thread can just reuse that computation because they're sharing the address space, right? So they can coordinate with each other and say, okay, oh, you have already computed it, so why do I need to recompute it? I can just reuse it. So because there's very fast inter-thread communication, they can do this. But if you implement these things as processes, then communicating is also very costly. So it may be cheaper to just recompute it rather than trying to get data from the other process, right? So that's web server, right? What are some other examples? Right. So instead of me telling you some examples of threads, I want you to tell me some, or imagine some examples where threads can be used. All right. So let's put this question to you. Yeah, please raise your hand to answer. Any ideas when threads can be useful? Any real world situation that you have seen yourself where threads are useful? Do you think they must be being implemented by threads? Okay, no answers. Nobody? Okay. All right. So let's say, I have an interactive program, right? So let's say interactive programs. Let's say, let me take one example. Let's say a game, right? Let's say network game. Right? Network game, multiplayer game, let's say. Right? So, one way to implement a network multiplayer game is that for every player in the, so let's say, this is a game which involves, multiple computers, and one player is sitting on each computer. Let's say there are 4 players, and 4 players, 1 player each is sitting on each computer, and they're playing the game, right? So how are they playing the game? Each computer is running a program, right? And the program that's running is running as a process, right? And now these process, so each computer has one process, and these processes are talking to each other using using network communication, whatever that is. Let's just ignore that, but they are talking to each other. But also they have to simultaneously update all the data on the screen about which process has which player has moved what, for example, right? Also, there have to be threads which are doing display, and there are threads which are basically taking your data, input data. Right? So one way to organize this is, let's say, okay, I'll have one thread per player, per other player. So this thread is just going to keep checking the other player's position, right? So let's say this one thread is checking P2's position, player 2's position, another thread is checking player 3's position, yet another thread is checking player 4's position, and all of them are updating a common state. This is common address space memory. And that memory is being used to update the screen to basically indicate the position of that player. Right? That's one way of doing it. It's a very simple way of doing it. That way, simultaneously, the threads can run, and simultaneously these threads can try to fetch information from the multiple players in the system. And yet another thread could be just taking let's say I'm also one of the players, then one of the threads could be just reading what am I typing on the keyboard or how am I moving the mouse, and display and updating my information. Plus that thread may be sending my information to all the other 3 computers, right? So I could have, I could arrange my program as a multi-threaded program. One thread for every task that is going on simultaneously, and these tasks are supposed to communicate with each other in a very fast way. So that's the reason we're using threads and not processes. So we need concurrent or simultaneous execution, right? And we need very fast communication. So in all these examples, basically, we had simultaneous or concurrent, also called concurrent. Right? These are pretty much similar execution words. And secondly, I needed fast whatever. And let's say I was calling it inter-process, but in this case it's inter-thread communication. They should be able to communicate very fast. If one thread updates a state, it should be visible to everybody immediately. Right? Okay. All right. So this is all nice, but we said that one needs to be careful about when you are programming with threads, because when you are programming with processes, for example, if you wrote your own small program to do something, that program doesn't need to worry about anybody else in the system, right? They could be running, but they're running in their own address space. I don't care, right? But if I'm using threads, and let's say my program has 2 threads, then I need to know, oh, by the way, there's another thread that's running and that may be updating the same data that I want to read. And so, I hope that I don't read half written data, or, I have read only when the other thread has completely written its data, and so on. Right? So I was using the example of one student in one room versus multiple students in one room. Right? So if you have multiple students in one room, then they need to coordinate with each other so that one doesn't spoil other person's data and all that. Okay, there's an answer from CEM. Says in Microsoft Word, auto spell checking is an example of multi-threading. Okay, yeah, that's quite likely happening through a thread. So there's one thread in the background that is just doing spell checking, right? So there's one thread which is taking your input and displaying it on the output, right? So it's, let's say, taking input from standard input and displaying output on standard output. And we have seen such a program, right? Shell was one such program. But then there's another thread which is just doing spell checking. Very good, right? So there's an answer from CEM. Thanks, CEM. So CEM says auto spell checking. Right? So yes, I mean, example of thread example. Yes, good. Why do you think this is likely to be implemented as threads? Number one, the spell checker needs to know what is the data of the document. And so to be able to know the document, it must share the address space. Right? I mean, it's much faster to share the address space than have a separate address space and then have this process communicate and copy my data to that data. That's going to be much slower. Rather, just have a thread which is able to access my documents data right there and then as soon as I'm typing it. Right? So it's better to use a thread to do that. Very good. All right. Okay. So but when you're doing threads, you have to be careful that, for example, in the case of spell checker, I should basically not run spell checker till my full word has been typed. For example, just a not a realistic example, but let's say you want that the whole thing should have been typed before you actually start executing your algorithm, which does spell checking. Right? So this kind of coordination is also called synchronization. Right? Okay. So synchronization basically means that if there are multiple threads, they need to indicate to each other that, look, I'm now accessing this, you are not accessing this, and so on, right? So they, before they do something, they have to in some sense get permission from other people that, look, I'm accessing it, and please don't bother me in the middle or something like that. So it needs to some flags to basically say, look, I'm accessing. So for example, if I'm in this room, I have I have, let's say, put a lock outside the room that saying that, look, I'm using this room, so please don't just keep coming in the room while I'm using this room. Right? That's coordination. That's synchronization. Right? How does synchronization work? Okay. So let's first take an example where if there was no synchronization, then things will become very bad. Okay. So let's say let's take the example of a linked list. Right. So I assume all of you are familiar with the linked list. You have studied it in your data structures class. Right. Very simple data structure. And here's the linked list. It says, okay, there will be a head pointer. Okay. And this will be the next pointer in each element, right? This is next pointer, and at some point it will be the null pointer. Right? So that's a linked list. Right? Assume all of you are familiar with the linked list. All right. So let's say let's write some code which is going to, let's say, insert an element into this linked list. So one way to insert an element, let's say there's a function called insert. Right? And let's say insert basically takes element. Let's say I want to insert a data. So let's say the data is an integer. Let's say this is 4, 5. Or let's say, I want to represent a string as a linked list. So let's say I want to say IIT Delhi. So it's I, E, and let's say last word is also IIT Delhi. Now I say I want to insert another alphabet called, H. Let's say. So let's say I want to insert another alphabet called H, and let's say each element has one alphabet in this structure. So I say insert H, and I'm going to say, okay, how do I insert H? Well, first I will say, let's say list. Let's say this type is list. So list star L is equal to new list or malloc list, whatever you want to say. Right? So you're going to allocate some data, the new, and then you would say L dot data is equal to H, right? I'm going to say L dot next is equal to what? Let's say I append it in the beginning, so I say L dot next is equal to head, right? What else do I need to do? I say head is equal to L. Right? This is nothing. Right? So head is equal to L. So what will happen? I'm going to create a new element. I'm going to put H into it, and I'm going to put its next pointer to point to head, right? And then I'm going to remove head and put point head here. That's what I'm doing. So I've inserted into the linked list. Right? So these three statements, I first allocated a new element, that was this element. I've made its data to be equal to H because I wanted to insert H. I pointed its next pointer to whatever was the previous value of head, and then I renamed head to point to this new element. Okay? I assume everybody understands this. So this code is correct, all right? So this inserts an element into the list in the front. But let's say, this list was was in the same address space, and there were two threads that call insert. So let's say, so let's rewrite this. So there's insert, says L is equal to new list, L dot data is equal to H, right? L dot next is equal to head, and L head is equal to L. Right? This was our code. Right? Let's say this was executed by thread 1. Thread 1 executes this code, insert, and these are these 4 statements that thread 1 is executing. Right? Now let's say there's another thread T2 that also wants to insert to this list. Right? So it also calls insert, but let's say this was inserting H, and the other thread wanted to insert E, or let's say I. So he wanted to say hi, right? So he said the first thread is going to say H, and the second thread is going to say I. All right, so the total should be high. So so it's, once again he's going to execute these 4 instructions. He's going to say L is equal to new list, L dot data is equal to I, L dot next is equal to head, and head is equal to L. So same code in both sides. Okay. Now let's say this thread is executing on CPU 1, and let's say this thread is executing on CPU 2. Right? So they're simultaneously executing, right? And so what can happen? What are some possible outcomes? Outcome is, let's say this thread started executing first and finished all this, and so H was added. So let's say H was added first, and then this thread started to work, and then I was added, and so the final output is IH, right? So I pointing to H. That's one output. If let's say thread 1 executes before thread 2. Go. If thread 1 executes after thread 2, then you get H and I. And let's say both of these are acceptable as long as, so let's say you are just adding these characters, and all you care about is that these characters should be there on the list, and you don't really care about the order. They should be there on the list. They shouldn't get lost, right? They were just basically storing this data in the list. But let's say what happens if they start executing at the same time, and what happens is that this guy says new, he also says new, but they get different elements. So one of them gets one element, the other gets another element. He says H, he puts H in its own element, he puts I in its own element. He makes next point to head, he makes next point to head. So let's see what happens. So let's say it's possible. So in this case, one thing happened before another thing. In the second case, this thing happened before this thing. But let's say they both happened like this, right? So they got intermingled like this, right? So then what can happen? Well, let's see. It can so happen that E1 creates one element called L1. E2 creates an element called L2, right? E1 puts H into its element. E2 puts I into its element, right? E1 says my next pointer should point to head. Okay. E2 also says I want to point my next pointer to the same value head. Okay. And now the T1 says, now let's update head to point to L1. And now T2 says point head to L2. Right? So what kind of structure you have? You basically have a structure where there is, this, actually it's no longer a list. Now there are two elements that are pointing to the same next element, and one of them is not even reachable from head, right? So if I were to draw, let's say this was my list earlier, right? And let's say this was head. What I wanted was, now correct execution would have been either L1, L2, let's say this is A and D, so let's say A and D. This would have been correct. Another thing that could have been correct was this, head, L2, L1, A, D. Right? But what happened in the third case was that they got intertwinkled like this, right? And so what happened was something like this happened. Head is pointing here. It's pointing to L2. L2 is pointing to A. That's pointing to B. And now it's going null, let's say. But there is this other element that's also pointing to A. But nobody is pointing to it. Right? So this is L1. Right? This is incorrect. After all, I wanted a list, and this is not a list, number one. Number two, one of the elements that I had inserted is no longer reachable. If I was to search for this element, let's say I was to search for this element I, then I'll never be able to get it because I'll start from head and I'll only see 3 elements, whereas there should have been 4. Right? So if I start from here, from head, I'll see element number 1, element number 2, and element number 3. There is no pointer from A to L1. So I'll just go straight from here and I'll only see 3 elements. Right? Because I'm assuming it's a linked list. So this one is basically as good as useless. Right? This is not reachable from head. And that's incorrect, completely incorrect. So the code that we had earlier, it was working very nicely if you had only one thread. But if you have 2 threads, then this code is incorrect because sometimes it produces correct answers and sometimes it produces incorrect answers like these. Okay. Right. So at this point, I'll open the floor for questions. If there's anything unclear, please ask me. It's important that you understand what this problem before I discuss the solution. Okay, any questions? Can check on questions. I assume everybody understands it. If there is any question or if you are not understanding something, yeah, please feel free to ask me at this point. Okay. All right. So let's look at this example again. What happened was 2 simultaneous threads were trying to update the same data structure, and so that data structure became corrupted. Right? It's no longer in the shape that you wanted it to be. You wanted it to be a linked list. Now it's not looking like a linked list, and some elements are just hanging around which you didn't want. Right? Let's take another example. Right? Let's take a more concrete example. Let's say I am a web server. Right? And I want to know how many hits have occurred. Right? Hits basically mean how many times this web page has been accessed today. Right? Let's say I'm running this IIT Delhi's website and I want to know how many people access this web page. Okay, there's a question from LNMIT. Let's look at this question. So he's saying that let's look at this linked list example once more. Okay, so all right. So before I go to the web server, let's look at the linked list example once more. So let's say, so here is the thing. Let's say I had a linked list. Okay. The linked list is supposed to be this linear structure that goes to null and has a head. This is an example of a linked list, and let's say the first element was A and the second element was B. Okay. Now, if I wanted to insert something in it, let's say I want to insert C, then I would execute these 4 instructions called, L is equal to new list, L dot data is equal to C. I'll say L dot next is equal to head. I'll say head is equal to L. Okay. So that will insert the data into the list. I hope you understand this. Right. If you don't, then please ask me now. Right. So if you don't, please type a question in the question tab. Right. So assuming that you understand this, then let's say there was another thread running simultaneously which wanted to say insert D. Right. It's going to do the same thing. It's going to say L is equal to new list. Right. It's going to say L dot data is equal to D. It's going to say L dot next is equal to head. Right. And so the head is equal to L. Okay. Now we said that look, if these codes execute one after another, so let's say this code executed first, so let's say this is T1 and let's say this is T2. So what are the possible states of the list after both of these threads have executed? Right. So if let's say T1 executed first and T2 executed second, then what will you get? You will have a list which looks like it will first insert C, and you're going to get a list like this, right? And so earlier the head was pointing here, and then T2 will execute, and now T2 will execute and it will insert D here, right? And it will point D to here, and now finally head is going to point here. We're going to say get DCAB. Okay. If on the other hand, so this is T1 first, T2 second. On the other hand, if it was T2 first, T1 second, then what would you have? Oh well, you would have, let's say it was A, B first, so this remains just like that, right? And head was pointing here earlier. Now T2 gets to execute, and T2 is going to insert D. So it's going to put D here, and head is going to point here now. And now T1 will get to run, and T1 will insert C. So it will push C here, and head will point here. Okay. Just compare these two. In this case, in one case it was CDAB, in the other case it was DCAB, right? Okay. And what if T1 and T2 execute in interleaved manner? What is interleaved manner? Something like this, right? So let's say there are these 4 instructions. T1 executes before T2, it's this. T2 executes before T1, it's this. And if they execute in interleaved manner, it's this, right? So if they execute in interleaved manner, which is also a possibility, then what am I going to have? I'm going to say, okay, there was A, then there was B, okay, going to null, and now T2 is going to point to, let's say it created an element called L2. So this is D. And simultaneously, T1 is also going to point to the same element, unfortunately. Okay. And then you're going to say head is equal to one of these, and let's say the head points here. So this is the structure you're going to get if they execute in interleaved manner. And this is incorrect, right? Because firstly, this is no longer a list. Secondly, this element C is not reachable. If I just iterate from head, I'll never be able to reach C, right? Because arrow is going from A to C or D to C. Arrow is coming from C, but that's not useful, right? So this is not reachable. This is an error. Right? Okay. So what does it mean? It means that the threads should have coordinated with each other such that one way is that you please look at, so one way is that you disallow this kind of execution, right? You either allow this or you allow this, but you never allow this, right? One way to do that is that when the thread is doing something on the list, the thread sets a flag and says, okay, I'm operating on the list, so you have no business on touching the list now, right? So in which case, even if it tries to execute at this point, it's going to say, oh, I cannot execute in the middle. It will come and execute later, right? Okay. Let's take another example, and that was for the web server, right? And let's say I was interested in counting the number of hits, right? And so let's say there's this global variable, an integer called hits, right? And there are multiple threads, right, which are executing request. Thread 1 executing request 1, thread 2 executing request 2. Okay. So now at the end of the request, thread 1 wants to say, okay, it says hits is equal to hits plus 1. Okay. Similarly, at the end of the request 2, thread 2 wants to say hits is equal to hits plus 1. Okay. So what should happen if both of the threads have finished? Finally, the sum effect should be hits is equal to hits plus 2. Okay. That should have been the final effect. But I'm going to show you that it's possible that if these threads execute simultaneously, then the final effect is not hits is equal to hits plus 2, but can be something else, right? So let's see how what it can be and why. Once again, let's say this is thread 1. It says hits is equal to hits plus 1, right? And let's say this code gets translated into 3 instructions. First instruction is load hits into register R. It's a register reg. Okay. Then you have add 1, I'm going to $1 by indicate that it's a constant to reg, right? Then I'm going to say store reg hits. So one statement like this gets translated to 3 instructions like this, right, in assembly code. Okay. So this is correct code if there's only one thread executing. But let's say if there were 2 threads executing, right? So let's say the first thread, so this is thread 1 and says load hits into reg, then says add 1 to reg, say store reg to hits. Right? And here's another thread T2 that executes, let's say, the same thing. Right? That executes load hits into another its own reg, with reg 2, right? Because each thread will have its own private registers. Let's assume that. Right? But hits is common. Hits is the common shared variable, global variable, and reg is some private local register. Right? It's going to also say add $1 to reg to the store reg to hits. Now once again, if you say T1 first, T2 second, what is the final value of hits? Let's say initially the value was 0. Let's say initially the value of 0. Then what's the final value? 2. Okay. Let's say T1 first, T2 first, T1 second. Then what's the final value? Once again 2. But what if they were interleaved? If they are interleaved, then what will happen? This 0 will get loaded into register in thread 1, but register is private, right? So this is CPU 1's register, this is CPU 2's register. So registers are separate. Similarly, this one's register will get loaded, so it will be, this will have R gets 0, this one will also say R gets 0, then it will add 1 to register, so R will get 1, right? And this one will also add 1 to the register, so here also R will get 1. Right? And then you're going to store register to hits. And so what are you going to store? You're going to store it to be 1. And what are you going to store here? Once again 1. So what's the final value of hits? 1. A big problem, right? You wanted to count the number of hits, but if these threads are executing simultaneously, it's possible that you're miscounting, right? These are problems with threads, and these are very similar to the nature of problems that you see when you have roommates sharing the same room. It's just like saying you started you started some job, and let's say you unplugged some computer, and then somebody come and you started opening the computer and doing something, and then another person comes and he plugs the computer and you get an electric shock, right? It's similar to that, right? So you basically want to say, look, I'm trying to repair the computer, I have unplugged the computer, so while I'm repairing the computer, please don't touch the computer, right? So in a physical setting, you will probably just communicate to him that, look, I'm doing something, please don't touch it while I'm doing it, right? But in an operating system, we need to have ways of one thread telling the other thread that I'm doing something. While I'm doing it, please don't interrupt me, right? Or please don't touch the same thing, right? Otherwise, we are both going to get a shock, right? So that's what's happening. In the case of a linked list, what I wanted to say, so let's say this is my linked list code. I wanted to say that while I'm executing these 4 instructions, please don't ever execute these same 4 instructions at the same time. While I'm executing it, wait for me to finish and then execute it, right? That would have solved the problem. Okay. Similarly, in the case of hits, I could have said, these are the 3 instructions executing. Let me first finish these, then I'm going to execute these. Right? So these thread 1 should be able to tell thread 2, look, I'm working on hits, please don't touch hits while I'm working on it. Then once it has worked on it, then thread 2 can work on it, right? So this way of doing things is basically what's called is done through locks. What's a lock? Basically say that thread 1 says take a lock, so it says acquire lock L. Then you can call insert D into, let's say, head, and then you can say release lock. Right? So these are two functions called acquire and release that will disallow another thread from entering insert while the first thread is executing an insert. Right? It's similar to saying that I'm talking in this room. I put a lock from inside of the room so that nobody else can come into the room while I'm working. Once I'm done, I will open the lock. That's release. Okay. So if there are multiple threads running and they want to access the same data, the same variable, they should first try to acquire the lock for that variable. If the lock has already been acquired by somebody, then it will have to wait till the other person releases the lock. And once it has released the lock, then I will get a chance to acquire it. And the guarantee is that while I have acquired the lock, nobody else can also acquire the lock. Right? So a lock can only be acquired by one thread at a time. The semantics of acquire are that it will try to get a lock on this data, and it will say, okay, I'll while I'm doing it, I can do whatever I like with it. It's like it's my private area. Now once I have released the lock, then somebody else can start working on it, and I don't mind. So for example, if I did this, then let's say I always took and acquired and released lock, then I will either have DCAB or ABC or CDAB, right? Never anything wrong, right? So I'll always have structures like this. So basically what I've done is that I have let's say I've said that this is allowed, T1 first, T2 second is allowed, because T1 can first take the lock and then release the lock, and then T2 can take the lock and release the lock. Similarly, T2 first, T1 second is allowed because T2 can take the lock and then release the lock, and then T1 can take the lock and release the lock. So this is also allowed. But T1 and T2 interleaved, this is not allowed, right? Why? Because if T1 has taken the lock, T2 cannot execute the same function at the same time. So till T1 has finished insert, T2 will not be able to run this code. Right? So this will be not allowed. And so that way I can make my program correct. Right? This way of, this is also called mutual exclusion. One thread excludes or prevents another thread from executing the same code. This, you exclude each other through locks, right? You say I'm executing something, so you cannot execute. So you exclude it. So I'm talking in this room. I have excluded anybody else from coming into this room, right? So that's mutual exclusion. Who came first doesn't matter. Let's say some other faculty member came first, then I would have had to wait outside the room till he released the lock. Right? So it doesn't matter who came first, but what matters is that while I am working in it, then nobody else can come till I'm finished. Right? So it's just first come first served, but whoever comes and whoever has the lock, nobody else can take the lock at that time. Okay, so I'm going to discuss more about locks next time, but I'll open the floor for questions. Okay, so there's a question from PSGCT. What is the race condition? I'm going to discuss it next time. Any other questions? There's a question from VPCOE. Like process, is there any need of a pipe-like structure for communication between threads? So the question is, do I need a pipe to communicate between threads? Well, the answer is no, not necessarily. Because you have the same address space, so you can just communicate by reading and writing to the same memory. So you don't need pipe, strictly speaking. Okay, more questions? Okay, so to finish, I'm going to say that there was a request that came to me saying that could you please provide a reference for the Unix system calls. So there's a book by W. Richard Stevens on, I think it's called Unix abstractions or something. Not sure about the name. I can confirm it and tell you next time. But this is a nice, very nice book for looking at Unix abstractions and studying them. So nice book for that. Also, you know, XV6. So on my course web page, you'll find some material for Unix abstraction. Okay. All right. And also, if you are an instructor in the course and would like to speak to me, please just send me an email. Right. And perhaps it will help if you could send me an email so that if there are any future announcements I have to make, for example, references or etc., then I can use your email address and send you an email. Right. So just send me an email saying that you are an instructor and you are an instructor for this particular college, and I'll save it and I'll use that to send you any information in future. Okay, if there are no questions, I'll stop. Thank you and see you on Wednesday.